Ladies and gentlemen, welcome to the second CLEO 2012 Joint Awards Ceremony and Plenary Session. Please welcome Paul Gildakis, CLEO Science and Innovations General Co-Chair.
Welcome, and thank you for joining us for the second plenary session of CLEO 2012. This morning, OSA and the IEEE Photonic Society will recognize some of their newly elected fellows, and we will present two distinguished keynote speakers. I've been privileged to work with a wonderful group of colleagues in preparing for this conference. Bob Fisher, my CLEO Science and Innovations General Co-Chair, the CLEO Quell's Fundamental Science General Co-Chairs, Wei Sao and Hideo Mabuchi, and James Tunnell, the CLEO Applications and Technology General Chair. I'd also like to recognize some of the individuals whose hard work over this last year has helped to make this conference so successful. Our thanks go to the 2012 program chairs for their outstanding effort. The CLEO Science and Innovations General Co-Chairs are Craig Arnold and Renee Jean Essiembert. The CLEO Applications and Technology Chair is Mike Raybeck. And the CLEO Quell's Fundamental Science Program Co-Chairs are Dimitrios Christodoulides and Norbert Lukenhaus. Thanks are also due to the members of the CLEO 2012 program committees. More than 365 members contributed to this effort over the past year. Together, the committee reviewed 2,367 submissions from 40 different countries and sessioned 1,301 oral and 367 poster presentations. In addition, there are 138 excellent invited presentations, including 26 outstanding contributed papers that were upgraded, 23 tutorials, and 19 short courses. This year, we are offering tracks in 15 CLEO Science and Innovations, 7 CLEO Quell's Fundamental Science, and 4 CLEO Applications and Technology topic categories. In addition, we are presenting 6 special symposia on topics ranging from space optical systems to quantum communications to one celebrating the 50th anniversary of the semiconductor laser. In addition to the program committee volunteers, we are also very grateful to the staff whose support has made our jobs much easier. If any of these volunteers or staff are in the audience this morning, please stand so that we may acknowledge your work. CLEO began in 1981 as a merger of 2 OSA IEEE meetings, CLEOS, the Conference on Lasers and Electro-Optical Systems, and CLEA, the Conference on Laser Engineering Applications, which had been alternating every other year. Ever since then, members of the optics and photonics communities have gathered annually, and the conference rapidly earned and has deservedly maintained a reputation as the premier international forum for scientific and technical optics. CLEO's program structure is designed to reflect the expansion of laser science and applications into new areas and to showcase the full range of topics from fundamental laser science to photonic applications to cutting-edge products. CLEO 2012 again offers high-quality content in 5 core event elements featuring breakthrough research and applied innovations in ultrafast lasers, energy-efficient optics, biophotonics, and more. From year to year, the field of optics and photonics makes dramatic strides. The cutting-edge research and applications discussed here are transforming society on many levels. This conference provides us with an opportunity to learn about the latest breakthroughs, to disseminate key information to the general public, and of course, to renew acquaintances with colleagues and collaborators. One of the main attractions of this conference is always the display of cutting-edge products at CLEO Expo. This year, we have 300 companies participating. 25% are from outside the US, which again reflects the global makeup of this event. The wide array of products on the show floor reflects the latest photonics applications and innovations in many industries, including biomed, energy, manufacturing, telecom, and others. Please set aside some time today or tomorrow to explore the CLEO Expo exhibit hall. A new component of CLEO this year is the Dine and Discovery event that was held, dinner networking event that was held this past Monday evening. I had the opportunity to join a group of people, professors, researchers, and students at the event that was held at the Gordon Biersch House on nano-optics and plasmonics. It was a very enjoyable evening of good discussion, good food, and good company. I hope that they continue this in future years and that you'll all have an opportunity to take part in that. I would also like to take a moment to recognize the conference sponsors: the American Physical Society Division of Laser Science, the IEEE Photonic Society, and the Optical Society. Thanks also go to our corporate sponsors. Their names are displaying on the screen. At yesterday's plenary and award session, we honored several colleagues who were named as award winners in 2012. This morning, two of our co-sponsoring societies will recognize some of their new fellow members. It's now my pleasure to recognize Hideo Kuwahara, President of the IEEE Photonic Society, who will introduce the IEEE Photonic Society's 2012 fellows.
Good morning, ladies and gentlemen. The grade of fellow within the IEEE Photonic Society recognizes extraordinary distinction in the profession. It is conferred only by invitation of the Board of Directors upon persons with outstanding qualifications and experience. Individuals selected will have made important individual contributions to one or more IEEE designated fields that have resulted in an improved quality of life for society. Not more than 1/10 of 1% of IEEE members may be elected in any year. This year, the IEEE elected 18 new fellows who are associated with the IEEE Photonic Society. I am pleased to recognize 6 of the 2012 class of fellows today. Please come up on stage as your name is called. Please hold your applause until everyone is on stage. The newly elected IEEE Photonic Society Fellows being recognized today are Brian Corner from the University of California, Davis, USA, for contributions to optical waveform analysis and Mode-locked lasers.
Thank you.
Mike Lee from Altair Corporation, USA, for contributions of the design of jitter test technologies. Mike, Mario Marconi from Colorado State University, USA, for contributions to the development and use of compact soft X-ray lasers. Chi Lin Pan from National Tsinghua University, Taiwan, for contributions to optoelectronic and liquid crystal devices for ultra-fast and terahertz photonics. Barry Shoup from the United States Military Academy for leadership in photonic signal and image processing for national security. Lim Pin Tsai from the National Instrument Technology Research Center in Taiwan for contributions to nanophotonics and near-field optics for microscopy and storage. Congratulations to each of you on behalf of the IEEE Photonic Society. OSA President Tony Hines will now announce the new OSA Fellow members.
Good morning, ladies and gentlemen, and welcome on behalf of the Optical Society. OSA members who have served with distinction in the advancement of optics are recognized by election to the class of Fellow. They are nominated by their peers, and their election is approved by the OSA Board of Directors. The number of Fellows is strictly limited to 10% of OSA's total membership. In 2012, OSA elevated 66 members to the rank of Fellow. The new Fellow members are recognized individually at meetings throughout the year. It is my pleasure today to recognize those who selected CLEO 2012 for the site of their presentation. I'd like to ask you to come to the stage when your name is called, and please do hold your applause until all of the fellow members have been called to the stage. The newly elected Optical Society Fellows being recognized today are Benoit Boulanger from the Joseph Fourier University, Institut Néel, France, for seminal and sustained contributions to theoretical and experimental nonlinear optics, especially the KTP crystal family. Lawrence R. Chen from McGill University, Canada, for contributions to optical fiber communications, in particular fiber Bragg gratings, optical code division, multiple access, and pulse shaping. Stephen Y. Cho from Princeton University for fundamental contributions to nanophotonic device and patterning. Stephen, unfortunately, is not able to attend today. A. Mark Fox from the University of Sheffield in the UK for significant contributions to the linear and nonlinear optical properties of low-dimensional and bulk semiconductors. Douglas P. Holcomb from LGS Innovations for continuing breakthroughs in the design and optimization of deployable high-power optical sources for challenging environments. Wilhelm G. Kenders from Toptica Photonics in Germany for founding and successfully running an optical company developing scientific and industrial-grade diode and fiber-based laser systems, as well as actively serving the optics community, and in particular the OSA. Hua Chung Kuo from National Chiao Tung University in Taiwan for leadership in high-brightness, light-emitting diode and vertical cavity surface-emitting laser education and technology. Hin Che Lei from the National Chiao Tung University, Taiwan, for his important contributions to the pioneering development of quantum soliton theories, experimental and theoretical investigations of new types of mode-locked fiber lasers and novel fiber devices. Miguel Levy from Michigan Technological University for outstanding and fundamental contributions in the areas of magneto-optic and optoelectronic films and extensions of the theory and application of magneto-optic photonic crystals. Henri Lezec from the National Institute of Standards and Technology for pioneering experimental and theoretical work in the study of surface plasmon polaritons and their application in nanoscience and metamaterials research. Xindi Li from Johns Hopkins University for innovative contributions to biomedical optics, especially in endomicroscopy and nanoBiophotonics technologies, enabling translational high-resolution and molecular imaging. Michel Meunier from École Polytechnique de Montréal, Canada, for fundamentals of laser materials processing and plasmonics and their applications in biomedical nanotechnology and microelectronics. Sergei Mirov from the University of Alabama at Birmingham for outstanding contributions to the development of novel vibronic lasers based on color center crystals and 2,6 wideband semiconductors doped with transition metal ions. Edward Ira Moses from Lawrence Livermore National Laboratory for outstanding technical leadership of the construction, completion, and use of the world's largest and most energetic laser system, the National Ignition Facility. Fiorenzo Ominetto from Tufts University for contributions in ultrafast nonlinear optics, photonic crystal fibers, and for pioneering the development of silk optical applications in silk-based photonic structures and devices. Miles Padgett from the University of Glasgow, the UK, for experimental and theoretical advances in the interplay of orbital and spin angular momentum of light and its interaction with matter. Clifford R. Pollock from Cornell University for significant and seminal contributions to the development of novel, tunable, and ultrafast laser sources for continuous dedication as an educator to outstanding teaching. Helena Rubinstein Dunlop of the University of Queensland, Australia, for pioneering contributions in micro and nano laser micromanipulation, including optical tweezers and atom optics. Helena is unfortunately not able to be with us today. Réal Vallée from the Centre d'Optique Photonique et Laser in Canada for leadership in expanding Canadian photonics academic and research infrastructure and for significant contributions to developing the first infrared fluoride fiber lasers. Wilhelm L. Voss from Universiteit Twente in the Netherlands for seminal contributions, both theoretical and experimental, to understanding of light propagation and emission in random and periodic media. Vladislav V. Yakolev from Texas A&M University for the development of new nonlinear optical techniques in diagnostics and imaging and their application to medicine and biology. And Xinning Zhu from Nanjing University, China, for contributions in engineering ferroelectric domain structures for quasi-phase match nonlinear optics, all solid-state multi-wavelength lasers, and quantum applications. It is my honor to extend very warm congratulations to each and every one of you on behalf of the OSA. Please join me for a very warm round of applause. I have to say this is one of the great pleasures of being OSA president, to recognize so much outstanding work. This concludes the award segment of the plenary session. Thank you all very much. Paul Judawalkis, CLEO Science and Innovation General Co-Chair, will introduce today's first plenary speaker.
Once again, good morning. One of the fastest growing areas at CLEO over the past decade has been the field of nanophotonics. In 2012, a total of 350 papers, or 15% of the total contributed papers, were submitted to the 2 CLEO subcommittees devoted to this area. In fact, this morning I was looking through the post-deadline papers and recognized that about 1/3 of the post-deadline papers are also in the field of nanophotonics. This morning, we are very fortunate to have a plenary talk from the leader of one of the key groups that is working to transition nanophotonic technology from the laboratory into commercial products. Yuri Vlasov is the manager of the Silicon Nanophotonics Department at the IBM T.J. Watson Research Center in New York. Yuri's biographical information is provided in the session program. In his talk today, Yuri will discuss Silicon Integrated Nanophotonics, Road from Scientific Explorations to Practical Applications. Please join me in welcoming Yuri Vlasov.
Okay. Thank you, Mr. Chairman, for introduction. Good morning, everybody. So I will talk about the road. And my first slide is showing kind of metaphor road. It's a yellow brick road, as you can understand. And I will follow with such kind of a metaphors through my slide deck. So the idea is we pass through some stages of this development. For me personally, this road started about 12 years back when I was hired at IBM to start nanophotonics work in T.J. Watson. And what I will present you, it's in no way can be viewed as a review of the efforts of all over the world. It's rather my personal experience as we were going along this way in this journey. So it may be not as well recognized, but silicon photonics has a long history. This is a famous picture that was made by Professor Abstreiter in Munich University and TU, Munich, quite some time ago, in '89. So it's, the history here is dated back about 20 years, and probably if you'll dig even further, it's even older than that. And the idea is we possibly can integrate optics and electronics on the same chip. In this case, it was bipolar transistors. It was '89, once again, no CMOS at that time. We can place fibers to it. We can direct light in the same chip. We can modulate this light. We can detect the light. And then we have some kind of a super chip which can make a lot of wonderful functions. And the whole motivation, the whole introductory sections of the papers at that time were almost the same as we are seeing today. So the idea is we can deeply scale the optics. We can place it in a standard microfabrication facilities that are used to build electronics. We are using exactly the same material set. It's silicon and germanium. Processing is the same, so it can be very, very cheap optics. So in some sense, looking now in where the field is, it looks like kind of a déjà vu. So all these motivations, all these aspirations, all this very hard work of the people at that time were devoted to exactly the same goal. So I will try to follow through this development, and maybe we can understand in the end why it's once again this big wave is now going. So one of the differences from this early years of silicon photonics development is in idea of optical scaling. So one of the first experiments that were done to try to make a waveguide in silicon is shown on the left-hand side, and what you see here is a waveguide which is formed by doping of silicon. So when you dope it, for example, with N+ materials, so you have a little bit different refractive index, and this can be used to guide the light. The refractive index difference, though, is very small, and therefore the size of the optical mode, which is calculated as shown there, it's about 100 square microns. Corresponding, since it is not a very high confinement, the bending radius, the critical bending radius of the waveguide, which finally will define the footprint of your circuit on the chip, is relatively big. It's 10 centimeters. So you can talk about single chip solution, but this will be probably of the order of the whole wafer. Another big advancement in the field happened somewhere in the 90s when SOI structures start to appear, SOI wafers. There you can isolate the optical mode from the substrate by using the thin layer of oxide and to have much higher confinement. The mode size is of the order of 5 microns squared, and the bending radius corresponding shrinking to 1 centimeter. Now we can talk about something more compact and maybe go along the way that was envisioned. What happened during the last 10 years is this idea of extreme confinement, of diffractional limited confinement, something that you can achieve with very thick boxes, the buried oxide layers, very specialty wafers developed for that, and very, very thin layer of silicon on top of the oxide, something about 200 nanometers. So in this case, the mode can be shrunk to something like 0.1 square microns. This is probably at the limit, if not the limit, of diffraction optics. Diffraction limited optics. And then you can really bend the light over very sharp corners of the order of 1 microns. Here we can talk about nanophotonics, about the size of the circuits which are much, much smaller than definitely than the wafer or even the die, or it can be comparable, as I will show you, with electronic circuitry nearby. Another structure which caught a lot of attention, and me personally spent a lot of time on developing this area, is silicon photonic crystal, because the idea was, okay, if we'll now go to diffractional limited structures, what is the ultimate limit to which you can scale the optical circuitry? And it was viewed that photonic crystals like that, which are built using the same technology that is used for CMOS, drilling holes in silicon slab like that, would allow you to shrink this mode size to even smaller. It would allow you to burn the light over very sharp corners. And then what you need is just to drill a sea of holes in your silicon and then carve channels in between where holes are missing. And this will give you the possibility to transport the light from one corner of the chip to another, to bend the light and to split it, and that was the idea. So it appears to be it is a very good structure. It is working as predicted, except that it's a very resonant structure. And as a resonant structure, it can work only in a very specific wavelength range, in this case defined by this bending of the curve. This, according to calculations, not all the spectrum along the y-axis is accessible for light. Most of it is actually leaking out of the slab, and only a small portion can still survive. So this is a kind of a visionary picture, if you wish, quote unquote, that I came up with when I was, it was my first year at IBM, and the idea was where we are going with all this nanophotonics approach, what we can think of this kind of a super chip. In principle, it's the same kind of motivation and inspiration that was given by the Abstreiter super chip model. Let's do something on a chip, something complicated, built in photonic crystals like Mach-Zehnder modulators here on the top, or some super prism WDM structures. We need to couple the light from the outside, so it's a fiber coming in. And what the idea is, let's just drill holes and then leave channels in between, and this will give us the happiness and will allow us to build such kind of chips. In principle, there is no meaning of this particular system. It's just a combination of complicated circuitry just to show that that's where we want to go. But that was an important stage, is to understand that that is practically the pieces of this mosaic, of this different components that we need to go over and try to develop in this technology. And that's what we've been doing since that time. And the first very important device is Mach-Zehnder modulator. So if you really want to use optics for something useful, we need to transfer information from electrical domain to optical. And Mach-Zehnder modulator is a standard device that can be used for that. So the light is coming from the left. It's coupled to the structure like that. In this case, it's photonic crystal. Since it's very small, very high confinement, it can be something like 17 micron only on side. It's split into arms, and one arm is modulated, for example, by injecting the carriers. And then on the output, you have ones and zeros in optical domain, so pulses of light. In order to develop such kind of structure, you need these components. You need fiber to the strip couplers, how you couple the light from big fiber to very small silicon structure with this 0.1 square micron volume of the mode. You need about 2 of them from both sides. You need 2 access strip waveguides that now transfer the light from the edges of the chip to your 17 micron structure in the middle. You need splitter and combiner in a photonic crystal. You need sharp band. You need phase shifter. You need to develop all this stuff, and it was not available at that time. It was a lot of theoretical work was done. It was predicted that it should work and very efficiently, but the question is now, if you want to do it practical, how you can do this. So the first question is how to couple the light in. And it was a big question, and still remains. And one of the solutions are shown on the right-hand side, which actually independently, several groups came up with the same solution of this inverted taper structure, which is now became very popular. And actually, by the way, the solutions that we developed at that time, we're using even today in our manufacturing runs. And the idea is just to taper this diffraction limited waveguide to almost nothing, and then the modes start to expand, and at some level it can meet the mode size of the fiber. So that was very important direction here, which is in principle not exploring photonic crystals, exploring this silicon photonic wire waveguides, if you wish, waveguides that are shrank to this diffraction limit, which was not the main goal. It was just a way to get access to this very beautiful world of photonic crystals. And that was the first, let me call it, integrated optical device, because here you can see several components which are combined together in one circuit, starting from this fiber edge coupler and going to the silicon photonic wire. There is a coupler in between wire and photonic crystal, and then going back. So that was an important achievement for us. It was actually reported as an internal IBM milestone at that time. So we can do it. We can do it with a standard tooling that are used in molecular electronics industry. But now the question is how we can go further from that. We just solved a very small portion of the problem. We went through a lot of exploration, how we can build splitters, how we can build bands in photonic crystals. And what we end up with, they do work as theory predicted. But they do work only for very specific resonance wavelengths. And it's not necessarily true that the resonance where the splitter is working is coincide with the resonance where the photonic crystal band is working. By definition, this is a resonant structure. So as such, it is first prone to it's working only for very specific wavelengths. And second, you need to align very carefully resonance in different parts of the system. So in principle, photonic crystals, the conclusion was, maybe it's not as good in making such kind of structures if you're looking from the application standpoint. For the modulator, what you need is something that is working for all wavelengths, not just for very specific, very narrow band. And that was kind of a revelation. That was something that was a result of a lot of work in IBM and elsewhere, and it was kind of a big leap in understanding what is possible and what is doable. And in principle, that is kind of another metaphor, cartoon. It's this kind of a moment of revelation, of something that you follow the road until the end of the world, and then suddenly some new horizons open up, some new idea coming up, and you are changing your view of the world. You suddenly have the door open into a completely new universe, and with new possibilities, with something that you never envisioned before. Probably that is the most rewarding moments that we'll have in this work, is to see that you can go over these barriers. You can break out of the sphere. So the same was here. So the idea is, maybe we don't need photonic crystal for all these components. Maybe we don't need photonic crystal anywhere else except maybe the phase shifter. Because that's where photonic crystal can play a role. That's where the resonant properties of the photonic crystal can be utilized very, it can be very useful property, because now you can shrink the size, because you can delay the propagation of light, you can utilize slow light in the photonic crystal. And when we built it this way, built on this new idea of removing photonic crystal everywhere else except the phase shifter, here it is. You see the splitter is done with the wires, the bands are done with the wires. The only place where photonic crystal is here. We found that actually we can measure the propagation of light through photonic crystal, and it appears to be associated with these very big dips in the transmission spectrum, which appear to be phase shifts. So each dip corresponds to pi phase shift. They are increasingly dense when you are coming to the edge of the transmission here. And if you expand it further, it's up to 300 fringes like that, which corresponds to very, very slow light that is propagating in the crystal when it interacts with the lattice. So this beautiful spectra is this new universe that opens. It's something that is predicted, something that was known from the theory. But when you finally see it from your experiment, from the experimental setup appearing this way, and what was predicted, now finally you can measure, you can touch, you can deal with that. That was very, very important and rewarding and interesting. But also along this way, since you were developing this, all other components, just trying to access to your treasure, to photonic crystal physics in it, we developed the other components which are just used as supporting materials, this silicon photonic wire waveguides. And they appear to be very interesting, although from the first point of view, it's kind of dull structure. It's just a bare silicon, is just a bar of silicon extended. But what is interesting is that it can bend the light maybe even more efficient than photonic crystal. The radius of the bands can be as small as 1 micron, and the losses are much smaller. And the footprint, by the way, is much smaller than photonic crystal. So that was kind of an unexpected result of all this exploration. And then you can build a lot of photonic structures on that, like splitters, resonators, the kind of WDM structures, and they all occupy a very small footprint. It is kind of a side product of research in photonic crystal, but it appears to be that this became actually the main road at the end. And then we came up with a new kind of vision, if you wish, where we can go. So once again, this system doesn't make any sense. It will not work at all. It's just, once again, the combination of some complicated elements trying to understand where we are going. What is the next step here? Once again, fibers are coming from both sides. Now we have multiplexing in it, so we can multiplex a lot of wavelengths on the same chip. We can demultiplex it on the same chip. We can switch it inside. And we can think about placing CMOS circuitry next to it. So VLSI portion of this chip corresponds to potential implementation of this stuff with the CMOS circuitry. So we were working hard on this photonic wire waveguides. There are interesting properties there. One of the ideas was to use the concept that is still very prolific and interesting and very popular, is to use resonators and ring resonators. And in this case, it's ring resonators that are used to enhance the delay that can be used as a delay lines for maybe some practical applications like optical processing. So in this case, we went actually to the limit. We made probably the biggest coupled ring resonator structure, about 300 of the strings coupled together. From one side, it was interesting to look where is the limit. I mean, how slow this light can be. Can we actually make this? But the second, it was an interesting exercise is just in fabrication tolerances. We are talking about nanophotonics. Can we actually yield all the structures? So we can do something with 200 rings. We can definitely do something very useful with one. That was kind of an idea. So we end up with the numbers that are kind of interesting. So we were shown that the delay can be achieved on something which is reasonable, about 10 bits. But also it was found from experiments, and which in principle is kind of an obvious conclusion as a result of experiment, because that was obvious from the beginning, from the theory. But one thing is when you are looking on theoretical predictions, another you are touching your hardware from the experimental setup. And the problem here is that bandwidth is inversely proportional to delay. So bandwidth delay product is constant. So if you want to have long delays, you have to have very resonant structures. That is obvious. You can play with some trade-offs here, but it's still fundamental problem for this kind of structures. And the second one, that the loss is proportional to delay. So you want to have very long delays through delay long bits, and it is inevitably associated with additional loss. So at some stage, the information is lost because the bandwidth is limited and the loss is pretty high. So then you can start to think from now the point of view of the application. And that was an important change in our direction and in my state of mind also in particular. So one thing, if you are looking on the physical problem, you try to understand what are the limits of slow light in photonic crystals, how the bands interact, all this beautiful physics which are hidden behind it you want to uncover. And then when you're writing a paper, you're writing an introduction section, which is like one paragraph saying, this can be useful for something like that, and then you get rid of it. So you're talking about what you're really interested in. But now when you're talking about, and you're trying to understand how to use all this physics in something useful, in some kind of applied area, like, for example, delay lines, you start to think, is it really introduction true? I mean, what are the trade-offs there? If you want to make a useful device, what are the trade-offs? What are the fundamental trade-offs? It's between footprint, loss, bandwidth, and delay. So how you can change all these arrangements that you can make a useful device? It appears to be, in this particular case, it's not very useful to go. It's not really a direction to make a delay lines because of these fundamental limits. But it was an important exercise. And it was an important change in the state of mind, because now for other devices, like, for example, modulator and based on PN junctions that are shown here, that still is a very intense area of research all over the world, and we are doing the same work here for a long time now. It is a fundamental trade-off that you first start to look at. If you want to make a useful device, you have to look for the parameter space, what you are optimizing. To make the fastest in the world modulator, that's important, but that's not all, because you have to understand that what are you paying for that? What are the, for example, intrinsic losses associated with the fast modulation of light in this structure? What is the footprint of the device? How fast you can modulate it? What is the thermal tolerances and fabrication tolerances? So in principle now, if you are talking about really trying to fulfill your goal to achieve this parameters, to go into this realm of this visions that you put forward when you started this work, you have to understand that the trade-offs actually might not necessarily result in some overlap of these parameters. Maybe the area where they can overlap is very small, if at all possible. So this exploration of this phase space, is it possible to make nanophotonic devices that can produce some useful function for something that is practical? That is a very different set of minds than looking on the fundamental physics. And it's an important direction here. So over the years, we developed quite a library of such kind of devices. So it's kind of in the realm of, I would say, applied physics area, but at the limit of optical scaling, with strong interaction with all these fundamental insights on optics at extreme scale. Starting from this optical buffer that I showed you, it's possible to use the same concept for very compact optical switches, for very kind of scaled down and very fast detectors, amplifiers, and germanium receivers. All this work makes sense, and it's a kind of very important stage over here to develop it. But then you come to a situation which is described by this very famous engraving. It's actually illustrating the book of Dante with famous words that midway through the journey of life, he found himself in the forest dark. So the roads start to fade. You are doing all this applied physics work, you have this library of devices. Are they really useful for some application? Can you actually do something with that? Or you can just continue doing the same way, just trying to look on different device applications, publish these nice papers, but what is the outcome of this work? Where is the impact? What is the next stage here? So the roads start to fade, and it was not clear how to proceed further, because and at that time, probably what we realized that actually we are in a big corporation with a lot of needs in practice. And the usual way of innovations that are coming from Yorktown, from research, fundamental research lab, is to go through a lot of stages of development into the fab, into the practical world. In principle, the road was always there. The question is, can we use it? What actually at the end of this road? What is useful for the world? What is the impact that this studies, scientific studies, applied physics studies, if you wish, can have on the real world, on the real application world? So there is one area which is several areas in the market that became very prominent, and they are viewed as a big impact on all optics research, community, markets, and industry. That's where big markets are expected, and they already started happening, and they expected even bigger increase in the nearest future. That is the main probably difference from the early days of the silicon photonics. It's not only the technology was not there, but also the market, the demand from the real world was not there. So what's happening now? There is one area where IBM is playing specifically a pretty big role. It's the supercomputers. If you look here, it's a share of their number of systems that are using IBM solutions in the top 500 list of the most powerful supercomputers in the world. And IBM has a big share over there, is playing a big role there, because that's one of their biggest businesses, is to use finally these solutions that are found in supercomputers in the high-end servers. And what is happening there can be illustrated in these two graphs. So on the left you see one of the supercomputer systems. It was the fastest in Europe in 2006, 2007, Mare Nostrum. It's Barcelona Supercomputer Center. It was built actually in the former chapel. You see here the floor where the racks are standing. So in principle you can view it as a high-end data center. If you look on any of the big data centers that Google or Facebook or others are building, it looks the same. It's a rack of computers which are going rows and rows over several kilometers now. So at that time it was the fastest computer. It performed at 90 teraflops, floating point operation for seconds. Now if you look on today's system, like shown on the right, and next to it is standing my colleague Alan Banner, who is the architect of the network and the system. The same performance is now obtained in one rack. So 90 teraflops are now coming from one rack system. It's a system that was released in August last year by IBM. So that's the sustainable growth of the computing power that is going. And in principle, there are problems associated with this growth. And the problems is not the performance of the system is no longer defined only by the number of processors, by the number of cores on the processor, but just the sheer amount of silicon around. But also how these components are connected together. Because this is a very parallel system. As you can imagine, all these racks, they should be connected. all the boards should be connected, all the cores should be connected, all the chips should be connected together, because that's the only way how you can distribute the computation in the parallel system. And then the computation is important, but that's not all. No matter how many processors you'll put in the system, it will be limited by the bandwidth in between them, how you connect the system together. And that's where optics start to play a very, very big role. This is just showing you this growth, the sustainable growth. It's taken from their website, as shown here, top500.org, which is tracking the performance of the fastest computers in the world. And you see here the performance in logarithmic scale from early days of supercomputing in 94, it's 100 gigaflops, which is probably now what you have in your laptop. The same performance. And once again, this was a big system. At that time, it occupies the whole building with a lot of cooling and power associated with that. And then in years, what you see is a sustainable growth, which now is reaching 10 petaflops. It's a supercomputer recently announced in Japan. And since it is very sustainable growth, you can expand it. You can just extend it. You can predict what will happen just 5 years from now. So 3 years from now, it is expected to have 100 petaflop system. And just by the end of the decade, it will be exaflop. So what is that? From some predictions of neuroscientists and system people, their human brain power is approximately in between 10 petaflops and 500 petaflops. It doesn't depend on IQ. It's just very difficult to calculate and to estimate what is the human brain power. Because it's a different algorithm, it's an absolutely different system, but somewhere in this range, that's where the human brain behaves. And we are talking about systems in the very nearest future, within a few years, 5 years maybe, that will be much more powerful than human brain. We already have this. If you think, I mean, your laptop is doing many things better than you, but now we are talking about the full, power of the brain. And the systems in exaflop will exceed that. And it is not something 40 years from now, like in a science fiction book. It's something that will happen by the end of this decade. And in principle, that is one of the demonstrations of such a possibility, which, by the way, is opening in new businesses and new markets. It's a recent contest between IBM supercomputer Watson on Jeopardy game. And Watson won in this question and answer game. And that was just showing that it is possible to design a supercomputer today that can beat humans, even in something that we believe is very human in nature, is trying to understand very, very intricate relationships between different concepts which are not necessarily can be formalized in a formal way. So this kind of a search and answer algorithms and the way how you connect this together, they all depend on how well the system is interconnected and how much, not only on how much intelligence you have in it. So what is interesting is that IBM is considering now this as a very important business area, because one of the possibilities to use this kind of a question and answer in supercomputer is to use it in medical diagnostics, for example. When you collect a lot of data from diagnosis from the databases, but you also can make a very complicated search of the information and come up with a decision. So you need that, you need this. And it can be done in a much more efficient way than spending hours and hours and days by humans to do the same. The same kind of a, question and answer and search algorithms can be used for market predictions or for weather forecasts. So probably we couldn't even imagine where it can be used further. It's just the beginning of this curve. So now if you look on the inside the supercomputers, what you will see is, for example, this is a Mare Nostrum system, and this is a floor, below the machine floor, where the cables are connecting the system together. And what you see here is not electrical cables, these are optical cables, these are fibers. And it's about 5,000 of them. If now move to the systems that was announced last year in August, it's one board of this size, and there are about several multi-chip modules in it, and this is a silicon chip sitting inside of it. What you see here is cabling, but once again, this is not electrical cables anymore. This is optics, this is fibers fiber optics that is coming directly to the chip, to this very small micropod, which is a product from Avago Technologies, which is co-developed with IBM, which allow you to transmit information from electrical domain from the chip into the optics in this fiber bundle. So this transceiver, which the only purpose of it is just to move information from electrical to optical domain. And when it is in optics, it can be transmitted either in between the racks or even longer distances, like 100 meters between different parts of the system. Now, if you look on the projections, so now 2008 was first petaflop computer. It was about 48,000 optical cables in it. 2012 is this year's 10 petaflop computers coming in. It's about 2 million optical links in this system. So 2 million, the whole worldwide volume of parallel optical modules is about several millions. So we are talking about one single system that can consume all the components today existing in the market. So it's really becoming a very big area for new businesses, for new markets. And if you look a little bit further in 2015 or 2020, we're talking about tens of millions or hundreds of millions of optical links in one single system. And that's just a necessity, because otherwise it's impossible to achieve exaflops. But what is important also is that the power and money you have to spend to buy, to use this optical interconnects is becoming a big portion of the whole budget. So it's about 20% of power is burned just on moving data around, and about 30% of the total budget, which is a lot. So that's the necessity to scale down power and cost of optical interconnects that would allow this system to exist. And the scaling actually is much faster than what is expected from the industry. We're talking about 10 times lower cost per gigabit each generation, which is much faster than what industry can provide. And that's where we need new technologies. That's where the current technology, which is mostly based on VCSEL multimode optics, is very difficult to imagine that it can provide these solutions. So with that, there is a new road now. There is a kind of a goal. There is something that finally you can see where you can use all your work for over the years, and you can try to build now systems that will answer on these challenges. So that was the work since, I would say, 2005. And once again, another kind of a visionary thing. We were preparing a big DARPA proposal in 2006, so we were thinking, okay, what can be DARPA hard? Let's try to put optics directly on a chip. We are not planning to put optics in the same silicon die as a processor or memory. That doesn't make much sense economically. In this case, what we were thinking, okay, there is a 3D technology that is in development stage. Let's think about using this technology to build this super chip where processor layer, which is has about 300 cores in it, is 3D integrated with a very short through silicon vias in between with the memory. And then on top we have our silicon photonics, which is just used for transporting light, for connecting this big computational power to the outside world. In order to do that, we need to build in optical layer, in one single piece of silicon, all these components that are used for long-haul communication, like SerDes, like amplifiers in CMOS area, plus detectors, WDM, switches, and all this stuff. And they should be much, much smaller than usual. They should be using the same approaches that we developed over the years to build scaled, diffraction-limited nanophotonic structures. So this was hard enough problem, and we are going along this way. So far, we haven't achieved it. But what is interesting, the 3D technology that in 2006 was viewed as a very long horizon is now in the products. And in the nearest future, we will see that even in consumer electronics, probably there will be a 3D stack of memory in it. So this is becoming a reality. 300 cores processor is becoming a reality. So there is a lot of progress done in many different technologies that allow us to think that maybe it's not such far in the future, this kind of a vision. So what we developed in order to make it, to make a next step in this road, we developed a technology now. So what you see here on the top is a flowchart diagram of the CMOS front-end integration. It's how the wafers are being processed in the CMOS fab, and they are moving from one set of tools to another. So the first one is you are building shallow trench isolation. It's when you etch silicon down to the box. Then you dope the structures in and build metallization on top. And that's the usual sequence of steps. What we developed over the years, in order to pursue our goal to have this monolithically integrated optical structures, we developed several processing modules that allow us to build side by side with the transistors, also optical modulators, detectors, and fiber couplers. So the same components that we developed before, but now we want to build it inside the manufacturing fab with all the constraints of the process, with all the constraints of the set of materials that you can utilize to build them. And this was a very big work. It's like took us about 5 years and it's not yet completely finished. But it is kind of a concept that allow us to think of very dense integration of optics and photonics when silicon transistors are occupying exactly the same silicon layer as the waveguides nearby. They are being processed with the same mask sets. They are being designed with the same enablement tools, like, for example, Anticodons. And at the end, what we'll have is very dense optical structures, like, for example, this in-resonator-based WDM, which occupies about 50 by 60 micron area, which is comparable, if not smaller, than the area that is occupied by corresponding CMOS circuitry, even in a very dense, very advanced CMOS nodes. So what you see here is a result of about 5 years of work that we finished by 2008. It was a feasibility study on the mask test site called SNIPER. Silicon nanophotonics integrated. I forgot exactly how we called it. But the idea is that what you look here is a photograph of the die with the ring resonator modulator in it, which is connected directly to the transistors. These are the modulator drivers, which are built side by side according to the flowchart diagram I showed you. And in the cross-section, it looks exactly as we discussed before. Now, this is another part. It's the receiver part. So the light is coming on this waveguide, is banded, and it's going into germanium detectors that we developed, which then collects very dim electrical signals, electrical currents, and amplify it in a series of amplifiers, TI-ALA circuitry here. And you see here also individual transistors. So this level of integration allows us to build much more complicated circuitry, like, for example, shown here. It's a 6-channel WDM transceiver, which combines both electrical circuitry, all electrical circuitry necessary to provide communication, plus optics, like WDM, 6-channel modulators, and 6-channel detectors. Since from the very beginning, we were looking in the limits of optical scaling, how small the devices can be, what is the smallest footprint you can obtain. The resulting technology with all this library allow us to shrink the size of these transceiver chips to something like, in this case, 3 by 2 millimeters. And if you think about, for example, terabit per second chip with 48 channels in transmit and receive, with all the optical circuitry and all electrical circuitry occupying it, with these densities, we can talk about area on the chip something like 5 by 5 square millimeters. It's not yet an ultimate limit. We can shrink it further, but then in principle it doesn't make much sense because the area on the silicon is becoming a commodity. It's not really a big portion of the final cost. So this is the plug that was given to the team members by IBM in 2008. We made it public in 2010 in press release. So it took us 2 years just to publish this stuff. And since that time, since this feasibility study, we were going through the same road, but now it's yet another stage of this development. Because now we have the feasibility study. It is possible to go into this market. It's a big gap, especially for people like myself coming from the area of science, fundamental science, maybe applied physics, but still it's a big gap to fill because now you're talking about different road. It's a road that is not connected with the trade-offs between loss, bandwidth, footprint, and do you want to publish in Nature Optics Express. It's rather connected with what are the applications, what are the products coming out, what are the markets, what is the cost associated with developing this product along this way, what is the pricing that you can charge your product at the end, and what is the return of investment And this you have to consider because it's absolutely different trade-offs, but they're absolutely important to understand what is the road ahead of you. Is there any road? And then there are a lot of other things on the right-hand side. I mean, if you are now talking about the product, that's the top-level hierarchy. And then from top down, from the product to design to component specifications, then you have to define what you have to achieve with your modulator. It's not a modulator the fastest in the world. It's now modulators that perform with specific functions meeting these specifications. So it's kind of the direction of sorts is completely reversed. It's now introduction that was before is now reversed. That's the body of your work. That's where the most of the focus is. So with that, we came up with this kind of a vision recently. It's published in Journal of Research and Development, IBM, commemorating 100th anniversary of the corporation. And the idea is that maybe this kind of a vision is still in the future. Not very far future, maybe 2018, this exaflop machine. But the intermediate step that we want to take with this technology is to build optics that can be put on board, on the same board as a high-end memory and processor, and taking the whole bandwidth that is coming from this board out into the outside world, either to the next board or to the next track. And that's where we believe that the first implementation of this technology is, and the products like that are already coming from other areas and from other companies. But what is interesting is that with our nanophotonics approach, and it was based on this fundamental approach, let's try to make things as small as possible. We end up in a very dense integration, something which is not achieved by anybody else before. And then we can think about this kind of a system, which incorporates all these components up to terabit per second in one single die. And it's now becoming feasible. It's not occupying the whole wafer as in the early days of silicon photonics. It can occupy now only 5 by 5 square millimeters on a die, even up to 48 channels. And because of this density, integration density is not really prohibitive, and it can go a little bit further. So I don't have much time here. We'll skip this part. What is just interesting? So the project itself is very multifaceted. It's not just material science, which is a lot of it, and I didn't touch on it, but there is a lot of material science, fundamental material science work involved in how to build the structures in a standard CMOS line. There are a lot of limitations on materials. There are a lot of problems in how to deposit one and another, how to etch, and everything like that. There is a lot of fundamental optical problems you have to resolve when you're now trying to meet the requirements for specific components, like for the modulator. There is area which I didn't touch at all, which relates to the CMOS design, because now you want to utilize the complexity of the CMOS circuitry that should be co-designed together with your optical components. And by this way, you can decrease the power, total power for transmission and the cost of the whole component. And this is part of the work that we've done over the years. It's just an amplifier for receiver containing several different circuitry over here. And this optimization, just to give you a flavor of the stages of this work, that's where we started in 2010. What you see here is the eye diagram. It's a complex function looking on how good the information is received on the receiver. Now, we're not talking about just detector. We're talking about a system, which is a receiver. So we're looking on how many errors this receiver can produce at this particular input on optical input and optical modulation format. So what you see here, the circuits initially were limited to something like 15 gigabit per second. Just a few months later, we came up with a new solution for the circuitry and redesign of the base detector. We came up to 20, and very recently we got to 28. And this is the work now, the last 2 slides in my talk. It will be presented in post-deadline session, where we are showing that with this technology we developed, we can go to 28 gigabit per second, which is very relevant to new standards for optical communications that are now being developed at IEEE. But what is interesting, it can go much further. It can go to 28, 32, and 38 gigabit per second. And this is kind of a heroic experiment where we showed that silicon photonics can actually receive signals up to 40 gigabit per second. This is heroic. I mean, it's kind of a little bit sleepy eye, but it's just showing that there is a room for improvement even further. So with that, I will conclude. So there is a road ahead. So far, the mission is set. The goals are clear. I'm pretty sure that in the nearest future, like 1-2 years from now, we will come once again into some kind of roadblocks, and the road will start to fade in the woods. But we passed through the stages several times, so I hope that we can go further. Thank you.
Yuri, thank you very much for that excellent presentation. On Monday, at the 50th anniversary of the Semiconductor Laser Symposium, I had the opportunity to listen to Marshall Nathan talk about the early days of diode laser development at IBM. And it's clear from your presentation, Yuri, that photonics is alive and well and thriving at IBM. We all look forward to the continued evolution of silicon nanophotonics into real-world applications in sensing, telecommunications, and exaflop computing. I'd now like to welcome Wei Cao, CLEO Quell's Fundamental Science General Chair, who will introduce this morning's second keynote presentation.
Okay, good morning. The second speaker is Matthias Fink. He's a professor at ESPCI Paris and also the director of Langevin Institute in France. He actually is a person with a super broad bandwidth. He covering all the way from acoustic wave to microwave and then to optical wave. So the subject of his talk this morning is time-reversed waves and subwavelength focusing. This may be a somewhat unusual plenary talk at CLEO because it will cover partly acoustic wave. But actually, the wave phenomenon is rather general, and the remarkable advances Matthias and his co-workers have achieved with acoustic wave can be a source of inspiration for us working in optics. So let's welcome Matthias Fink.
Thank you. It is a pleasure to be here, and I will make a presentation of what we are doing in our Langevin Institute in the field of time reversal waves. We have begun by working on ultrasound, and later we go to microwaves and now to optics. And I will show you the work that we have done with my collaborators. And as you will see, time reversal waves are quite different to what is called phase-conjugated mirrors. And there are some very nice specificity that can be used in a smart way. Let us begin first by the difference between different kinds of waves that we manipulate in our lab: ultrasound, microwaves, and optics. In ultrasound and microwaves, we are very lucky because we have arrays of antenna. It may be piezoelectric antenna or microwaves antenna, and we can do what we want with each antenna. Each antenna is able to transmit and to receive, and you can transmit any temporal modulation, and you can record the wave field in a linear way. This is quite easy to manipulate. In optics, things are much difficult because you cannot have antenna that are both transmit and receive, and if you want to make spatial shaping, you need to have some device like SLM. If you want to do temporal shaping, other device, and the detection of the wave field is a different story, and it can be done through holography or interferometry. Now, let us look at a very important problem, which is wave focusing. In physics, it is very usual, this problem, but you will see that it can be much more interesting when you try to focus a wave in an heterogeneous medium. If you work in homogeneous medium, you have the concept of length. You know that you can focus or a monochromatic wave or a pulsed wave. And you know that, for example, focusing monochromatic wave, it's interesting when you want to focus energy to do, for example, some therapy, or if you want to make imaging in a stationary mode. But you also want to focus pulsed wave, and this is done usually when you have antenna, for example, in the field of sonar or radar, and you can try to focus very short pulse, and application are radar, sonar. It may be therapy or it may be defense. You can focus strong electromagnetic pulse, or it's interesting in the field of telecommunication, where you want to send just at one position a short pulse and a series of pulses to send information. When you focus in monochromatic mode, you know all the diffraction limits. If you have an aperture, if you send just a sinusoidal wave, at the focus, what you obtain is just interference, constructive interference of all the wave. And if you look what you have at a point close to the focus, you have no more constructive interference, and you know, all of you, that the size of the focal spot is related to the aperture number and to the wavelength. And if you want to have a small focal spot, you need spatial diversity. Now, let us look at another problem. If you want to focus polychromatic wave through a dispersive media, if you have only one omnidirectional antenna and you want to focus on one point here, what you can do is that you can put on this antenna a combination of different time frequency, and your goal is to focus here just with one antenna. If you introduce, for example, a diffusive media, or if you introduce a cavity between the input point and the output point, you have a dispersive media. And now, because there are dispersion, you know that each frequency moves with a different phase velocity. And what you want is to obtain at this point exactly at the same time a constructive interference of all these waves. If you obtain this, just the addition of this will give you in the time a very short peak, which has a very high amplitude. And for doing this, you have to make a good combination with the good phase and amplitude of this wave. And this is a kind of very complex pulse that you send, very complex coda. And if you put this as an input, here you will obtain as an output a short pulse, very intense. This is frequency diversity, because you play on frequency diversity, you have no spatial diversity directly, and this is time focusing or time compression. Now, when you obtain time compression or time focusing, did you obtain at the same time spatial focusing? And to understand this, let us look at this example. You have a diffusive medium here, like in optics, but the medium is fixed in time. You send one frequency, just a sinusoidal wave, and you look in this plane what you have. You have a speckle pattern that depends on this frequency omega 1. And now send on the same medium another frequency, another temporal frequency, and you have another speckle pattern. And if you choose two frequencies that give uncorrelated speckle pattern, you have two different speckle patterns. Now send another color, another frequency pattern. And you have three speckle patterns. Now imagine that instead of sending just a sinusoidal wave, you send just a broadband pulse. It is a combination of all these sinusoidal waves, and each of them give you this pattern. But when you do the combination of all this, you have now a spatiotemporal speckle that changes during time. And if you look at one given time, what is this speckle pattern? It is like one of these speckles, but it is a combination of all this. And you can also look at one point at a given location, what did you receive during time? And at this given location, you receive a very complex coda in the time domain. Imagine that in optics, but it is easier to do this in microwaves or acoustic, you take this very complex pattern in the time domain. You take this, you time reverse this pattern, and now you applied at the source the time reversal of this pattern. If you do this, now your source, your omnidirectional source, send this complex waveform. It is like you send each of your sinusoidal wave with phase conjugation. That is to say, you phase match all these waves to obtain now, at this given point, at what I call the focal time, exactly a summation of all this pattern in phase. That is to say, at this point, at one time, you have time focusing, but you have also spatial focusing. And if you look, the size of a focal spot coming from this unique omnidirectional antenna, the size is of the order of the size of a speckled grain. This is spatial focusing, and the signal to noise between this and the background depends on the number of uncorrelated speckles you have created in your broadband. Here you see the combination of time focusing and spatial focusing. Now let us try, this was more signal theory point of view, let us go to more fundamental physics point of view. What is the connection of this with the concept of time reversal waves and causality? You know, if you want to focus a broadband wave in an heterogeneous media, you can do the following. You can try to build what I call the time reverse wave, but of course there is a causality problem, and I will explain you this on this equation. Imagine this is the case, for example, for acoustic. You have a non-dissipative medium, but heterogeneous, and you have a source, a point source at point R0 that sends a short click. You know, because of the time reversal symmetry that is here, you have a field which is called the Green's function corresponding to this point source, and you know that you have in fact two solutions on a mathematical point of view. You have one solution which is called the causal Green function that diverges from the point. It's a wave that diverges, and you have also another solution which is not good in physics but which is good in mathematics, which is called the anticausal Green function. It is a wave that begins before you put the source on, and it comes from the rest of the universe, it's focused on you. You will never see this because this is anticausal, and we select in our causal universe only this wave, the causal wave. A guy who likes to play time reversal, what he wants to do is to build an anticausal wave that will exactly refocus back at a point. If you can do this, you can have focusing without any diffraction limits. How to build this anticausal wave? And to do this, we develop in acoustic first the concept of what we call the time reversal cavity. It is to time reverse a causal wave field on the boundary. To do this, what we have done in the past, was the following. I think it will work like this. We have a source, and for example, we imagine that on the boundary, we put a lot of antenna. Each of them are reversible antenna that can be receiver or transmitter. We send a short click from one point. It sends a wave which is the causal Green function because we are in a causal universe. And what we do, whatever is the complexity of the medium, we record on each antenna the wave field. And we have, for example, many antenna, many analogic to digital converter, and we put all this information in memories. Once we have put all this in memories, what we do in a second step, we come back in each memory and we decide to read them by reversing the time chronology. We send what we receive first, last, what we receive last, first. And now we send exactly in a time reversal chronology this signal on each transmitter. Like this, we create a wave that is going backwards. Step by step, it's come back at the origin. But the problem of a wave is that a wave cannot stop. And this movie is not only the time reversal movie of this movie, it is followed after by a collapse and a diverging wave. And this is the origin of diffraction limit in wave physics. Let us look this in this example. Homogeneous medium, I send just a short pulse. If I use a time reversal cavity, I obtain a focusing pulse, converging, but it does not stop. It gives me after a diverging pulse. And in fact, there is an inversion of signal at the focus point. Now, imagine that instead of sending a short pulse, you send some oscillation, some wavelength. Look this movie. You focus, you think that you create only a converging wave. But no, there is the diverging wave, and the two interfere together. And if you just look what happened at the focal time, you will have just this. And this gives you the origin of diffraction limit. Diffraction limit is just due to the fact that if you are in free space, when you try to create a converging wave, there is not only a converging wave, but there is a diverging wave that comes after, and the interference between the two gives you the focal spot. If you have a sink that absorbs completely the wave, you can do better, and you can do diffraction. You will have no diffraction limit. Let us go one step more. Okay. Let us look what happens if you have not a complete time reversal cavity with many transducers, but if you have only a small aperture with some antenna. Take a source, send a short click, and here introduce a multiple scattering medium like a diffusive medium. And look what you obtain on each antenna. You will record a very long signal on each antenna because of the multiple scattering in the medium. Now, take this signal, time reverse them, and send back. When you do this, this is the experiment we have done some years ago. This was a random distribution of rods. We send a short pulse, and here we have an array of ultrasonic transducers made of 128 transducers. If you send this back in reverse, you have the nice surprise that you want. When you have sent your pulse, it was a short pulse, 1 microsecond long. Each signal record is very long. When you send them back in reverse, what comes back at the origin is time focusing. It is a short pulse. This is time focusing. Let us look spatial focusing. If you send a short pulse here, if you have just homogeneous medium like water for ultrasound, you have your antenna, you time reverse, you have a focal spot. Size is lambda f over d, like usual. But now, if you introduce here your diffusive medium, what you see is that with the same distance between the source and the antenna, now you record this complex signal. If you time reverse them, now the focal spot is 35 times thinner. Why? In fact, it is become, when you play time reversal, it is when you send a spherical wave here, all the spectral components that are going in this direction, the plane wave, are redirected by the medium here. And when you time reverse, it is the medium that becomes the lens. And now, even your aperture is small, spatial resolution does not depend on the array aperture. It is the diffusive medium that do the work for you. Now, in the first experiment, we have 128 transducers. Now take just one antenna, omnidirectional. Take this coda, time reverse, send it back, and look if the focal spot is focused. And you see that you have a focal spot, which is well focused. The side lobe is higher. Now, what is the level of these side lobes? In fact, it depends on how many uncorrelated speckles you average in the process of time reversal. And when you send, for example, a short pulse, you send a broadband pulse with this bandwidth. Now you want to know, in the diffusive medium you have, how many uncorrelated speckles. Sorry. I am going back. And in fact, the response is very simple. If you send a short pulse, if the pulse is spread in time, this spreading time is the tau-less time. And the frequency correlation that you have between two independent speckles has a size which is just the inverse of the tau-less time. And here you have 150 uncorrelated speckles in your beam. And it is why only one antenna works like it was 150 antennas. Each of them participate to the refocusing. Now, this is diffusive medium. Now you can play the same with a closed cavity that you can transform in a lens. Now, you want always dispersive medium, and this is a nice experiment we have done. We take a silicon wafer. It was a cavity for elastic wave, two-dimensional cavity, and we come with a transducer that gives a small punch here, 1 microsecond long pulse. And here, you excite all the eigenmodes of your cavity, and at point B, what you record is a very complex coda that has a long time spreading, typically 30 milliseconds. Now, if you take just a piece of this signal, it is like a random noise, 2 milliseconds long. This is called the Heisenberg time. It is the time you need to be able to resolve all the eigenmodes of the cavity. You take this signal, which is very complex, you time reverse, and now you applied on this transducer this time reverse signal. And it creates surface wave that will move, and you want to look if it's focused here. Before I show you the experiments, just what I want to tell you, point R sends a short pulse. The short pulse has a broadband spectrum, and in fact, you will excite all the eigenmodes of the cavity that correspond to eigenfrequency in the broadband spectrum. And what you obtain at point B is this very long signal, which is a combination of different eigenfrequency. And for each eigenfrequency, you have an eigenmode. For example, if you excite just at frequency omega 1, you have this pattern here. If you excite at frequency omega 2, you have this pattern, of course, and at omega 3. And each of these eigenmode structure is like a speckle, except it is not a speckle noise in terms of optics. It comes from the boundary of the cavity. Now, when point B time reverse this, and when you send in reverse on this point B, you can make a movie of the surface wave that you create inside your cavity. And from this point B, you see that this movie has the memory of point R. It refocuses on point R. And we call this a time hologram, because when you live in a closed universe, just what you record on one point is a complex interference pattern but broadband. And this contains all what you need to reconstruct back your object. Here the object was a point source. And now if you look what you have just at the focal time here, you have this pulse, and you see that just this coda, when you send back from point B, refocus here, and if you measure the size is half the wavelength you used. And in fact, what you are doing here, because you send a short pulse, you are creating at point B a combination of different eigenmodes. Here you have, in fact, in this cavity, excited 400 uncorrelated eigenmodes, and when point B sends this in reverse, at point R, all this mode add with perfect phase matching. And this is why suddenly you see a peak, and because of this, if you want to measure the size of a focal cell, of the focal spot, it is one modal cell, lambda over 2 typically. This gives you the limit. This gives you also the key if you want to do super resolution later. You will have to make eigenmodes pattern much thinner than the wavelength, and I will discuss this later. But do you think that this is useful? Yes, it is useful. We make a company of this, and it is a big success. Imagine the problem, the following problem. I have this table. I want to transform this table in a keyboard. And I am not very rich. I don't want to make sophisticated things. I just put a small piezoelectric antenna somewhere. And now I come at point R, I give a punch. And I record with this antenna, this signal, the hologram of point R, the time hologram, that I record. It's the green function that I record. If I take this signal, I can time reverse this. And if I time reverse, the table will move at point R. Not very useful, but we play with this sometimes. But we can do better. We can decide that we want to learn all the table. And we give punch at every point of the table with some spacing between each point. And we record in one memory all this green function. We record all the bank of time hologram. When we have this, we are happy. We come back one day after, and I give a punch on point B. Now, I look what my piezoelectric transducer receives, and I make a comparison with what I have in my bank of information. And I just do a time reversal experiment in the computer, which consists just to do cross-correlation of this with my bank of data. And of course, this signal will be very big, and I will recognize point B. But this is so powerful that look the product that we create from this. This is just a piece of glass, just the noise you are making with your finger, create always small acoustic source, and if you have recorded some of them, and if you have a fast correlator, when you move your finger, the system follows the trajectory. It's a kind of imaging. If you put 3 fingers or 5 fingers, you see 3 fingers, 5 fingers. It's a time hologram that you reconstruct, and this gives a nice company where we have products, and sensitive object was bought recently by Tyco Electronics, and we will go on the market to make many tactile objects which can have any shape, any size with this technique. Now, let us go to subwavelength focusing. Can we do better focusing that the basic limit lambda over 2? There are, in fact, two different approaches that we look in our lab. The first one was the SYNC, or the perfect absorber approach, where you have to introduce dissipation. I will put this later. The second approach that we begin later in the field of microwave is the idea, can we construct a medium made of subwavelength resonator like metamaterial that we put in the near field of the source? Let us look at this. Remember, we have a source sending a click, electromagnetic or acoustic or optic, and here we have a point where we want to focus. Usually, we put a diffusive medium between the source and the point where we want to focus. But now, imagine that this medium is made of subwavelength resonators with a mean distance much smaller than the wavelength we used. And imagine that instead of putting your source here in free space, you are moving this medium and you surround your source by this crazy medium made of subwavelength resonator. And imagine that the medium is not too big. I put a kind of scale, lambda, the wavelength you use. Now, if your medium is really ugly enough, when you send a short pulse in this medium, what you want is that the small medium is doing so much multiple scattering because you have subwavelength resonator. What will go out of this medium when you receive it is a long coda. You have dispersion, but that comes from a medium much smaller than the wavelength. And here you have to combine the concept of near field, optics or acoustic, and multiple scattering. Now let us look this more in detail. And this, of course, we play on frequency diversity, because in the far field you receive this dispersive signal. We begin by studying this with some of my colleagues in the field of electromagnetic wave. We were interested by the Wi-Fi frequency, 2.4 gigahertz, and the wavelength is 12 centimeters. Usually, an antenna may be a small wire. And what we do usually is that a small antenna may be a monopole antenna, and here we put 8 of these classical monopole antenna here that are classical source that send electromagnetic wave. But we decide to create this cap, which is really a strange medium made of many copper wire, randomly distributed at the beginning, and this very complex medium where the distance between two wires is 1 millimeter compared to 12 centimeters is a medium made of wire which are relatively long in one direction to be resonator for the 2.4 gigahertz in this direction. And now we put all this on the top of this antenna. Now let us look what we have. We have just this. You see this like a brush. And here you have, in fact, many small antennas immersed in this medium. Take the red antenna. Send a 10 nanosecond pulse on this antenna. It goes here, and now it is making multiple reflection, multiple scattering. And in the far field, you have telephone antenna, your smartphone, and you record this signal, which is spread in time. Now, make an excitation on just a wire very close at 4 millimeter, lambda over 30, and in the far field, the same antenna record a new pattern. You see that the difference between these 2 points is coded in this medium to give you 2 different time signatures in the far field. Now, take this signature, time reverse them from the same antenna, and look what comes back on red or blue wire. You have time focusing. All the energy is recompressed in time, but what is interesting is spatial focusing. Now, you refocus back in the medium on size, which is typically, in this experiment, lambda over 30. I will come back on this to explain why we do super resolution. When we found this at the beginning, we were not sure that it was reality, and we decided to push this to see if we can send information, typically a flower. We divide in 3 colors, and we decide that we will send on each small antenna, each of them at lambda over 30, one from the other, different information. If we put the antenna in a microstructured medium or not, In one case, you cannot send too much information. Here, you send a lot of information. In fact, with this technique, because you are able to focus on very small spots, you can increase the Shannon capacity that you can send in the medium, and you can use all the temporal code to send in parallel to each antenna some information. And from this, we have made a startup, Time Reversal Communication. It is now 40 employees, and it works with Bull to create this kind of process, but in a more elegant way. Now, let us go to basic physics. How it is working. You have your source, and instead of sending light directly in free space, you introduce this medium. In fact, this medium is a transformer. Usually, your source has evanescent wave, which remain close to the source, and propagative wave. Here, you create a transformer of evanescent wave in propagative wave. And in the far field, you record propagative wave. If you time reverse propagative wave, you send back in reverse, and there is a very nice theorem on spatial reciprocity that tells you that the propagative wave, when it comes back, it recreates the evanescent wave, which was at the origin of this. But did this thing is very efficient? Not sure. You think that this kind of antenna is really not efficient and not so powerful. In fact, it is very efficient. Let us understand why. What is the mechanism that transforms evanescent wave into propagative wave? I call this the multimodal board. You know that if you play violin, if you have only your string sending sound, you don't receive any sound. The level is very small. But because the string is close to a board in wood, suddenly there is a resonance, and your antenna becomes very effective, and you receive a lot of sound. Here, let us imagine that our medium is not random, but periodic. We have many copper wire, and we introduce a small source very close to this wire. And this source sends a short pulse. Now this medium, which is made of many wires, has many eigenfrequency and eigenmodes. And in fact, in the far field, you record a long signal, as I explained, which contains a spectrum very rich, coming from all the eigenfrequency of the medium. And we will understand this a little bit better, how it works. Two key points to be efficient. The medium must be made of coupled subwavelength resonator. Here you have many resonators. One resonator that I call an atom, because for me an atom is a subwavelength resonator, but here our atom is for electrical field, one copper wire. One copper wire resonates at frequency F0. Now you couple many of these resonators, which are very close one from the other. The second thing is the medium must be of finite lateral size. Here it was lambda over 3, but it can be lambda typically. Now you have many of this wire, and it is like you have one frequency for one resonator, but many resonators all coupled to them give you a set of eigenfrequency and eigenmode. This medium now has, if there is n resonator, it has n eigenfrequency that correspond to n eigenmodes, which are complex electrical patterns that exist inside the medium. Let us look this more in detail. Sorry. Hold on. No. Sorry, I am going. Okay. Okay. Look this medium. This kind of medium, there are transverse electromagnetic waves in this kind of medium. And if you look, for example, one wire was at frequency F0. It is the resonance frequency of one wire. When you put all these wires together, suddenly you create many kind of oscillation inside the medium, and you create here this kind of dispersion curve, which is very well known in many fields. And what you see is now that the medium has many eigenfrequency between F0, the basic frequency, and low frequency, and at each eigenfrequency, the medium oscillates spatially in this direction with pattern. Here the pattern is a pattern where the distance between two oscillations is smaller than lambda. Here it is even smaller, smaller, smaller. When you are going to higher frequency here, close to F0, now you have pattern oscillation, eigenmodes, where the distance between each of these out-of-phase oscillation is the distance between two wires. And you have a collection of eigenmodes that you can create in this medium. Now, if you put a short pulse here, the short pulse has a large bandwidth. The bandwidth may be between F0 and nearly F0/2. And this short pulse will excite all these eigenmodes in the medium, oscillating at different eigenfrequency. And each pattern is like this. Now you ask, all these eigenmodes are evanescent because the distance between 2 points that oscillate in phase opposition is smaller than the wavelength. Usually, this must not radiate. Why did it radiate? In fact, if you have just a finite size medium, you ask, did this medium, where the pitch is λ/20, is able to radiate outside? In fact, if you take the same medium, just take this, but make it infinite size. Try to see if a pattern where you have λ/20 is able to radiate. All of you know that it does not radiate. Why? Because when you have this pattern on the x direction, you can go in the Fourier space. You know that you have what is called a propagative window that tells you that only propagative wave has oscillation less than λ/2. And now if you take the Fourier transform of this is an evanescent component, and this will never radiate because your medium is infinite. Now look here, just look this size. This size, it is the same medium, except now it has a finite dimension. That is to say, the Fourier transform is not a Dirac, but it has a sinc evolution, and now you see that this part radiates. This is in the propagative window. Because of the corner, the system is able to radiate. And now it radiates. Okay, you are happy, it radiates. But did it radiate with efficiency? Now what is interesting is the following. Look, for example, at this frequency, close to the resonant frequency in this experiment, the pitch was λ/70. It means that you are very far from the propagative window and you have only a small radiation outside. But if you have small radiation, it means that the mode loses its energy very slowly. That is to say, the energy is trapped in the medium. If the energy is trapped, there is a strong resonant amplification inside the medium, and this is called the Purcell effect. Now, if you look another oscillation at a lower spatial frequency, it radiates better, and you don't need the same amplification. But what is nice is that all these eigenmodes, even there are evanescent eigenmodes because we are finite size, and because you have resonant amplification, they radiate all with the same efficiency. And in the far field, each mode sends its own information. You have a very efficient antenna working at all the eigenfrequency of your spectrum. And now, if you put your small source here, you send your small signal. In the far field, you record this signal, and if you make an analyze, you see all the eigenmodes. And you are happy because when you time reverse this, when it's come back, you create a combination of all the evanescent eigenmodes. And because the spatial oscillation is very fast, you create subwavelength focusing, typically λ/25 in this experiment. But what is nice is you have only one antenna. You don't need to put antenna in all the room. Just one antenna made the work because you have this medium here. Now, let us look if this can be done in acoustic. Can we build subwavelength resonator? In acoustic, bottle of wine and of champagne are good Helmholtz resonator. The problem is that they are very dissipative. But what is the best, and this was demonstrated by Fabrice Lemoult and Geoffroy Le Roset, is to use cola can, or any kind of can, are very useful. It is typically 6 centimeter diameter, and this is a resonator for sound frequency corresponding to wavelength of 80 centimeter. That is to say, one Coke is smaller than the wavelength you used. And here, look this experiment. We have a crystal of soda can, and you just send a sound, large bandwidth on one point, And the medium is making a lot of reverberation in it, and in the far field you record this kind of signal. And you can look the spectrum and you see many eigenmodes, but here you have dissipation and you don't see all the eigenmodes what you want. And if you just do time reversal from some loudspeaker and if you look what comes back, instead of having a focal spot of lambda over 2, you have a thinner focal spot that focuses on one soda can. And you can do better than time reversal, because time reversal used the concept of without dissipation. If you have dissipation, you can do iterative time reversal to learn how to reinforce the higher spatial frequency to refocus better. Now, this was one way to do focusing. Now, let us come back to some very important physics. Another way to super resolution is to introduce the sink. Remember, the problem in free space is that when you want to focus, you create a converging wave, but it is always followed by a diverging wave. And the interference between the two gives you the focal spot. Even if you have 4 pi aperture length, cavity, Maxwell fisheye, it's always the same problem, lambda over 2. Now, let us look, how to go. Let us look at a nice experiment that we have conducted in our lab. The idea was, when you focus a wave, at one point, there is a diverging wave. But at the source point, we create what we call the time reverse source that sends exactly the same wave, but out of phase. In this case, the two waves will be completely distracted. You create anti-noise, and like this, you create only a focus on one point, without diffraction limit. We have done this experiment with this elastic cavity that I present you at the beginning, and the idea that when point B was sending back in reverse the signal coming from point A, when it was coming at point A, at the good time, point A must send its own pulse. And if you compare the two patterns, here this is what you obtain when you have the time reversal of the source, and here it is what you obtain when you have just the field time reversal. You need to time reverse both the source and the field. And if you measure the size of the focal spot, it was lambda over 14 in this experiment. Now, it's interesting to understand the mathematics. When you have a source sending a wave, you must write the wave equation with a source term on the right part. Here, if the wave was diverging wave, the causal field that you create from a source with some time modulation. If you want to create the anticausal wave only, you want to create phi of r minus t. That is to say, you have to replace t by minus t here and t by minus t here. And because the wave is time reversal symmetric, you will obtain a new equation for the time reverse wave, the converging wave, that is this. But here, don't forget that the source must also be time reverse. This is what I call the sink. You have, if you really want to create just a converging wave, which is not followed by a diverging wave, you have, when you time reverse the wave field on the boundary, also to time reverse the source. This is what I call a sink. This is an active sink. You have to send energy at the good time, and it is not very practical. But it works. Some people discovered this 1 or 2 years ago. It was the group of Leonard, and they called this a drain instead of a sink. But because my name is Fink, I want that the sink remain. And just to come back, now, this is very interesting because it tells you that if you really want to beat diffraction limit, you have to create, when you focus, a sink at the focal point. Now the sink was active. I was injecting energy. Now, one very interesting question is, can we build passive sink? That is to say, can we replace an active source of energy that cancels the diverging wave by just what we call the perfect absorber? And this idea was is now strongly related to the work of Hui Xiao and Douglas Stone. It is the concept, what they call time reverse laser. They found this very interesting idea that a source can be, for example, a laser. A laser is a Fabry-Perot cavity, a resonator which has some gain. And you know that when it is working, it sends energy, a wave in one direction and even in two directions if you have not fully reflective boundary. Now, they imagine the following idea. This is a system which is a resonator, that is to say, it sends monochromatic wave at some frequency outside. Now you want to time reverse this movie. You send exactly in reverse these two waves, but because the medium has gain, what is the time reverse of a gain medium? It is a loss medium, and the loss must exactly compensate the gain in a time reversal operation. And if you have a good loss, when you send these two waves, they will interact and nothing will be reflected. You have a perfect absorber. And a perfect absorber is very nice, but the problem of this perfect absorber is that it works only for monochromatic wave. When you send them, and this is in 1D, but you can imagine to do this in 3D with a perfect absorber. But the size of the perfect absorber must be big enough to resonate, that is to say, at least lambda over 2. And you are always diffraction limited. You can build perfect absorber, and now the question is the following. Is it possible to build a black body, because a perfect absorber is a kind of black body, but for broadband signal, is it possible to make a passive black body whose size is smaller than the wavelength? And this is an open question, and in my opinion, it's not easy, because causality come here to broke this. And what you can imagine is to have a diffusive medium, like many subwavelength resonator, plus some very absorbing spot. And if you play with this, you can do exaltation of the field if you play in a clever way. Just to conclude, all this was an ultrasound, microwaves. Now, the question is it possible to time reverse visible light? It is interesting because it is not like phase conjugation. Just one point, if you send the good pulse shaping in the time domain, can, through a diffusive medium, focus. And there was now at least 3 very nice experiments, perhaps I forget some of them, which was conducted in different labs. One in Israel, in the group of Silberberg, one in France with Béatrice Châtel and Sylvain Gigant from our lab, and one in the group in Holland of Ad Lagendiek, to try to pulse shape the wave that is matched to a diffusive medium in order to focus where you want. And the concept of super resolution can also be think in terms of visible light. Can we create subwavelength resonator, which can be plasmonic cylinders that are put all together, and there will be a nice paper in Nature Communication that Geoffroy Le Roset, my co-worker, has done to show that we can also, at least in simulation till this time, use this concept. I just want to finish by telling you that this week in Nature Photonics we have a review paper on controlling wave in space and time for imaging and complex media with my colleagues, and this will give you some more information on what I say. Thanks.
Thank you. Matthias, thank you very much for this enlightening presentation. So the time reversal techniques that Matthias and co-workers have developed for the acoustic wave and microwave can now be adopted for optical waves thanks to the very rapid development in nanophotonics as shown by the first speaker this morning. So next, Hideo Mabuchi, one of the CLEO's Fundamental Science General co-chairs, will provide some closing comments and thoughts.
Thanks. I hope you have enjoyed our 2 plenary presentations as much as I have. I think they both really did a great job of showing the dual role of new applications and new fundamental concepts in really moving our field forward. Before we wrap up, I'd like to once again congratulate our distinguished colleagues who were elected to fellowship in their societies. And I'd also like to encourage you all to visit the exhibit floor across the street to check out the new products from the exhibitors. You have exclusive session free time to visit the exhibits this afternoon between 12:30 and 1:30, and again from 3 o'clock to 4:30, and tomorrow from 10 a.m. to 11:30 a.m., and also 1 o'clock to 2 o'clock p.m. And finally, remember to mark your calendars for CLEO 2013, which will be held next year from June 9 to 14 back here in San Jose. This concludes the session. Thank you very much for attending.